Hello, today we will be doing section 10.4 comparison tests. So in the previous sections we were looking at when does a series converge and when does it diverge, and we have a few tests already. So we have the following tests. Test for convergence of a series. So first you have two series or families of series that we immediately know if they converge. We have the geometric series. We know that the geometric series converge if the absolute value of r is less than 1. We also have the p-series. We know that the p-series converge if p is greater than 1. The next test that we looked at was the nth term test for divergence. And this didn't tell you if a series converged, it only told you if it diverged. If you got that the limit of an as n goes to infinity equals 0, then it could converge, it could still not converge. So this was kind of an inconclusive test, but it's still a useful test. It's an easy thing to do to just immediately see, oh, it has no hope of converging, so I'm not going to continue. We then looked at the integral test. So when you see a series and I ask you, does this converge or diverge? The first thing you do is you look at the first two bullets. Is this a series that I just immediately know? Is this a geometric series or a p-series? If it is, then you know if it converges or not. If it's not, you move on. Then you should always do the nth term test for divergence. Normally very easy to do, and if the limit does not equal 0, then you're just done. It diverges. If the nth term test for divergence is inconclusive, then you move on to other tests. We looked at the integral test, and this was really useful if the sequence that we are summing up in the series is something that we could integrate. So now we're going to look at, okay, well, what if we couldn't integrate this very easily? When we were talking about improper integrals, and that's what the integral test does, is it compares an infinite series to an improper integral. When we were looking at improper integrals in section 8.8, we used a comparison test. The comparison test was compare this function that we know how it behaves in an improper integral to this function that we don't know how it behaves in an improper integral. And in the comparison, we figure out something about that second function. So we have something very similar for series. So we have the direct comparison test. The direct comparison test says if you have a positive sequence an that is bounded above by another sequence bn for every point after some given point capital N. So this inequality only holds in the tail is really what this is saying. And this capital N has to be a positive integer. Then we have two results. One, if the summation from n equals 1 to infinity of bn converges, then the summation from n equals 1 to infinity of an also converges. And two, you have the opposite. If n equals 1 to infinity, the sum from n equals 1 to infinity of an diverges, then so does the sum from n equals 1 to infinity of bn. And we saw pictures of this back in 8.8 about why this is true. And really we have the same thing here, the same pictures. Instead of drawing a smooth curve, you just have a collection of dots. So let's see this in action. Example. Does the summation from n equals 1 to infinity of 1 over 2 to the n plus n converge? Solution. So we go through the tests. This is not a geometric series. This plus n makes it not geometric. This is not a p-series. This 2 to the n makes it not a p-series. We do the nth term test for divergence. The limit as n goes to infinity of 1 over 2 to the n plus n equals 0. So the nth term test is inconclusive. We then look at this. All right, could we do the integral test on this? I do not know how to integrate this function, so we do not want to do the integral test. So we move to the comparison test. So the idea is we want to compare this to a function that we know how it behaves. To do this, what we do is we ask ourselves, what is the dominant term here? Here, 1 over 2 to the n plus n will be determined by basically whatever term is largest. And that is the 2 to the n part is the largest, so it's determined by 1 over 2 to the n. So we want to compare one over 2 to the n plus n, the sequence that we're interested in, to 1 over 2 to the n. All right, so first we need to set up that inequality. 0 is less than or equal to an, less than or equal to bn. So we note that 2 to the n plus n is greater than 2 to the n. You're adding something positive, so it's going to be greater. Take the reciprocal, and we have 1 over 2 to the n plus n is less than or equal to 1 over 2 to the n. Okay, so if we wanted to use the comparison test, based off of those two options, the only thing that would give us a result is if the summation of 1 over 2 to the n converges. If it diverges, then the comparison test, the inequality is going the wrong way. Well, we know that the summation from n equals 1 to infinity of 1 over 2 to the n, this converges. Why is that? This is a geometric series. Cool, so our function that we're interested in, or our sequence, is bounded above by something that converges, so this must also converge. So by the comparison test, the summation from n equals 1 to infinity of 1 over 2 to the n plus n converges also. So the general strategy for using a comparison test is you try to answer what is the dominant term here. If you figure out what the dominant term here is, and then your inequality behaves correctly, then you should be able to use the comparison test. So let's do another example. Does the summation of 1 over n squared plus n plus 1 converge? So I'll let you guys do this. Pause the video and try this. And when you're done, unpause it and see if your answers agree with mine. So looking at this, the first thing you do, this isn't a known series. So you use the nth term test for divergence. The limit of 1 over n squared plus n plus 1 will be 0, so the test is inconclusive, so we move on. We're going to do the comparison test. We ask ourselves, what will dominate? And here, the n squared will dominate n squared plus n plus 1. So we want to compare to n squared. And really, we want to compare to 1 over n squared. All right, so set up your inequality. N squared plus n plus 1 we're adding something positive, so this will be greater than n squared. Take the reciprocal, and we have the sequence we are interested in is less than the sequence 1 over n squared. And the summation of 1 over n squared, this converges because it's a p-series with p equals 2, which is greater than 1. So the direct comparison test tells us that our series also converges. Not too bad. We're going to do another example. This example, so the previous examples, we just had things in the denominator, and we were looking at what dominated in the denominator. This example is going to do a little bit more complicated of a sequence to see how we would handle something with a numerator. So does the sum, the square root of n to the 4th minus 1, divided by n to the 5th plus 3 converge? Okay, so solution. We're going to do the same thing we did before. We're going to look at what are the dominant terms. This time we have to look at the dominant terms of the numerator and the denominator. So the dominant terms are in the numerator, the n to the 4th is going to beat the negative 1. So we have the n to the 4th, but it's still under the square root. The denominator, the n to the 5th, will win. So we have divided by n to the 5th. And this is just 1 over n cubed. So we want to compare our sequence to 1 over n cubed. And this inequality is a little bit trickier, but it's still not too bad. So we compare to sum of 1 over n cubed, and we know that this series converges by the p-test. In other words, it is a p-series. So we set up our inequality. We have an, what we have, the square root of n to the 4th minus 1, divided by n to the 5th plus 3. And we need to somehow get it to 1 over n cubed. Well, first off, we want to get n to the 4th in the numerator. Here, we are subtracting off 1. So if we add that 1 back, then we have something larger. So this is less than the square root of n to the 4th divided by n to the 5th plus 3. And that's just n squared over n to the 5th plus 3. And we're going to say that this is less than n squared over n to the 5th, because if the denominator gets larger, then that means that the whole expression gets smaller. So if therefore the opposite direction, if the denominator gets smaller, so going from n to the 5th plus 3 to n to the 5th, then the whole expression gets larger, hence this direction of the inequality. And that is 1 over n cubed. So we have an is less than 1 over n cubed. So the comparison test, the direct comparison test, says that the summation of the square root of n to the 4th minus 1 divided by n to the 5th plus 3 converges. We can use the direct comparison test for things that aren't polynomials. We've basically just been using polynomials for these examples, so let's do a quick one without a polynomial. So does the natural log of the summation of natural log of n over n converge? So solution, the dominant term is natural log of n over n. There isn't really anything to cancel, and that doesn't really help us because we don't know if that series converges or not. That's what we're trying to figure out. So what we do is we try to compare this to either a p-series or a geometric series. The obvious choice for a p-series is 1 over n, since the denominator has an n. So we compare this to 1 over n. And we know that the summation of 1 over n diverges because it is the harmonic series. Okay, now we need to set up the inequality. The natural log of n over n. Well, we want to compare this to 1 over n. And we know that the natural log of n grows fast, well, eventually is greater than 1. So we just know the natural log of n is greater than 1 at some point. In fact, I think this is for n greater than 2. Let's check that. Yeah, for n greater than 2, where n is an integer. So we have that our sequence, natural log of n over n, is greater than a sequence that when you add it up, it diverges. So that means that the direct comparison test says that the summation of the natural log of n over n diverges. Okay, one more example, and this will lead us to the next comparison test, because the title of this section is comparison tests, plural, so we need to have another one. So example, does the summation of 1 over n squared minus 1 converge? All right, solution. The dominant term is going to be 1 over n squared. So we want to compare this series to the summation of 1 over n squared, which converges. It's a p-series with p equals 2. So what we want to show is that 1 over n squared minus 1 is less than 1 over n squared. So let's try to do that. Well, we know that n squared minus 1 is less than n squared because we're subtracting off something. Take the reciprocal, we get that 1 over n squared minus 1 is greater than 1 over n squared. Well, that's very unfortunate. This is the wrong direction of the inequality. The wrong direction to use the direct comparison test. So we need a different method. So if you recall what we did in section 8.8 with improper integrals, we only really cared about the tail. We only cared about how is this function behaving, how is this area, because we were looking at integrals, the area under the curve. How is this area behaving with very large values of x? If you start at a very large value of x and go off to infinity, so how does it behave in the tail end? And the way we talked about that end behavior was with a limit. We looked at the limit as this tail goes to infinity. And here, that's all we really care about also. If you have a finite number of terms in your sum, then that's going to be a finite number. It could be a really large finite number, but it's just a finite number. So we only care about that tail and what's it doing towards infinity. So we can also look at limits. So how did we phrase this with the improper integrals? That was the limit comparison test. So the limit comparison test says, suppose that an is greater than 0 and bn is greater than 0 for all n. then if the limit as n goes to infinity of an over bn equals c, with c not 0 and not infinity, then the series, the summation of an and the summation of bn, they either both converge or they both diverge. Again, this is saying that if the end behavior of both the series an and bn are the same or multiples of each other, where it is actually a multiple of each other, then they're going to behave the same. They're either both going to converge or both diverge. So example, let's finish that example that we started. Does the summation of 1 over n squared minus 1 converge? So as we said, we want to compare this to the summation of 1 over n squared. So we take the limit as n goes to infinity of what we're interested in, 1 over n squared minus 1, divided by what we are comparing it to, 1 over n squared. Reduce this fraction. This is the limit as n goes to infinity of n squared divided by n squared minus 1. These both have the same degree, so this is just 1. And the coefficients are both 1. 1 is not 0, and it is less than infinity. So the summation of n squared minus 1 also converges, since this sum converged by the p-test. So we were able to use the same comparison, but by looking at limits, we were able to, we didn't have to worry about which direction the inequality was going. Okay, now let's do another example. That one wasn't too hard, so let's ramp it up a bit. Does the summation from n equals 2 to infinity of n cubed minus 2n over n to the 4th plus 3, does this converge? So, as always, we need to determine what we want to compare this to. So we want to determine what dominates in the numerator and the denominator. Well, n cubed minus 2n over n to the 4th plus 3 is approximately, the n cubed will dominate, so that's approximately n cubed in the numerator, and it's approximately n to the 4th in the denominator, since that will dominate. And this reduces to 1 over n. So we compare this to the summation of 1 over n, which diverges. Again, 1 over n is the harmonic series. Okay, we use the limit comparison test. So the limit as n goes to infinity of what we're interested in, n cubed minus 2n over n to the 4th plus 3, divided by what we are comparing it to, 1 over n. This is the limit as n goes to infinity of n to the 4th minus 2n squared, divided by n to the 4th plus 3, which again, these have power 4, the degree 4, sorry, with coefficients 1. So this limit is just 1, which is finite. So by the limit comparison test, the summation of n cubed minus 2n over n to the 4th plus 3 also diverges. And let's do one more example just to wrap this section up. Does the summation of 10n plus 1 divided by n times n plus 1 times n plus 2 converge? So I'll let you try this one. Why don't you pause the video, try it, and then unpause to see if you got it right. All right, so we need to determine how we think this will behave. So 10n plus 1 divided by n times n plus 1 times n plus 2 is approximately the 10n will win in the numerator. And then we have an n from here, an n from n plus 1, and n from n plus 2. So we'd expect the denominator to behave like n cubed. This is 10 divided by n squared. So we expect it to behave like 10 over n squared. So we're going to compare to the summation of 10 over n squared, which converges. It's a p-series. So we set up the limit. I'm going to write the limit a little bit different, just because that's a lot of nested fractions. So we're going to divide by 10 over n squared, which is the same thing as multiplying by the reciprocal. So times n squared over 10. The 10 will cancel with, oh, can't do that, never mind. Almost made a horrible mistake. But the n in the denominator will cancel with 1 power of the n squared. So that will be 10 n squared plus n divided by 10 times n plus 1, n plus 2. That's 10n squared plus n divided by 10n squared plus 30n plus 20. And that limit is just 1, which is finite. So by the limit comparison test, our summation also converges. So before finishing this video, I'm just going to point one thing out. Notice in all of these examples, I've been very explicit about why things converge. So I said compare this to the summation 10n squared, 10 over n squared, which converges because of a p-series. And then coming down here, yes, I set the limit, but I explicitly said the limit comparison test says that this series also converges. If we scroll up, you can see I did that up here in the previous example. I said 1 over n, the summation of, diverges by the harmonic series. So then we're using the limit comparison test to say it diverges. So make sure you also do that when you're writing out solutions. Make sure you are explicit about why series are converging or diverging. Is state the test. You can use the abbreviations I'm using, LCT for limit comparison test. Scrolling, I said DCT for direct comparison test. You can use those abbreviations, but just make sure